Look at a digital 3D model of a mechanical gear. To turn that mathematical geometry into a solid, heavy steel physical component, data must cross a massive operational chasm. In a traditional manufacturing environment, crossing the gap between a digital file and a finished physical part requires layers of manual human intervention. Engineers have to calculate and route toolpaths by hand. Machinists must manually calibrate and set up the cutting equipment. Operators are required to physically transport heavy raw materials from storage to the floor. To eliminate these structural bottlenecks, industrial engineers developed Computer Integrated Manufacturing, or CIM. It is a unified system architecture designed to integrate and control all independent manufacturing processes under a single computer network. To understand how modern production scales, we have to track exactly how raw geometric data is translated systematically into automated physical action. The ultimate goal of the modern factory is to shift the bottleneck of production away from manual physical labor and replace it entirely with seamless information flow. This diagram shows the complete architecture of a computer-integrated manufacturing system. It is broken down into distinct functional subsystems that surround a central management hub. The digital thread of any manufactured part originates here, in the product design sector. This is where computer-aided design, or CAD, takes over. It provides the software environment used to generate precise geometric models, construct wireframes, and run finite element engineering analysis to test structural integrity. Despite the highly advanced interface, this initial phase still relies heavily on a human engineer to conceptualize the product and draft the complex geometry. A CAD file perfectly defines the geometry, dimensions, and material properties of a part. But it contains absolutely no instructions on the actual processes required to build it. Without a precise execution strategy detailing the required cutting tools and feed rates, the most rigorously engineered CAD model is entirely useless to a physical machine tool. To cross from design to execution, the network uses an algorithmic bridge called Computer-Aided Process Planning, or CAP. It adapts digital geometry to the physical constraints of manufacturing. CAP executes this translation by utilizing a foundational organizational logic known as group technology. Group technology categorizes components into distinct part families based on shared geometric shapes, like cylindrical shafts or prismatic blocks. To make these attributes readable, coding systems assign alphanumeric values. A monocode assigns fixed digits in a hierarchy, while a polycode tracks independent variables, like material requirements. Applying this code structure means the system rarely plans a new part from scratch. The computer instantly recognizes when a new gear requires the exact same sequences as an older component. By recognizing that similar parts require similar processes, group technology converts the creative problem-solving of process planning into a highly repeatable mathematical formula. To physically output these instructions, CAP utilizes two distinctly different architectural methods. This flowchart illustrates the retrieval CAP system. Relying on historical data, a user enters a part number, and the algorithm searches its database for the part family. Standard routing operations are retrieved and lightly edited to accommodate minor variations, outputting a finalized process plan. By contrast, this diagram illustrates the generative CAP system, creating process plans entirely from scratch. Generative logic cross-references the coded part description against a live database of available machine tool capabilities, using hard-coded rules to calculate optimal cutting sequences dynamically. While the retrieval method relies on mimicking the past decisions of human engineers, the generative system achieves true automated synthesis of manufacturing logic. With the routing plan formalized, the digital data moves out of the planning systems and enters the physical manufacture quadrant of the factory network. Computer-Aided Manufacturing, or CAM, translates the CAPP sequence into specific execution codes. These are highly specific instructions, like G-codes, that dictate the exact linear and rotational motion of cutting tools. These execution codes are fed directly into the physical hardware of the factory, the numerical control, or NC, machine tool. Modern automated machining centers utilize closed-loop feedback systems. Encoders continuously monitor the physical position of the cutting tool and relay that data back to the control unit, correcting microscopic alignment errors in real time. To operate effectively at an industrial scale, Factories implement direct numerical control. A central computer orchestrates dozens of independent machines simultaneously. We see this coordination deployed on heavy automotive assembly lines, where arrays of integrated robotic arms weld and assemble massive chassis parts in perfect synchronization. The exact same principles of central control also govern the high-speed fabrication of intricate microscale electronics components. At this stage of the framework, the unpredictable variables of human manual operation have been replaced entirely by the absolute precision of digital execution. However, perfectly automated machining arrays will halt production immediately if starved of raw materials or choked by a buildup of work-in-process inventory. The CIM network solves this through an automated storage and retrieval system. The core structure consists of vast vertical storage racks separated by defined aisles. Mechanized stacker machines navigate these exact aisles, retrieving inventory and transporting it to designated pickup and deposit clearance zones. The factory network uses this system as a dynamic buffer. It carefully tracks production rates to time the exact delivery of work-in-process components between distinct machining operations, preventing bottlenecks. By integrating logistics into the central computer, the movement of heavy steel operates at the exact velocity as the digital data driving the factory. Zooming out to view the integrated architecture, we see how these subsystems connect. The digital thread is complete. CAD design geometry is translated by CAP logic, driving the physical execution of CAM, all continuously supplied by the automated logistics of the ASRS. There is one final step that closes this operational loop: computer-aided quality control. Using automated contact inspection, finished parts are physically measured. That strict tolerance data is then fed continuously backward into the systems management hub to actively refine future production cycles. Implementing this framework comes with massive friction. It requires incredibly high initial investment costs and demands complex software integration, where a single system failure can compromise the entire production line. Against those costs, the integrated network yields enormous advantages in pure productivity, nearly eliminates human manufacturing errors, and centralizes enterprise data management. Most importantly, it generates absolute flexibility. Because the hardware is driven by programmable data rather than fixed physical tooling, a massive factory can pivot its operations to entirely new product designs almost instantly. By linking design, planning, and fabrication into a single closed loop, computer-integrated manufacturing upgrades the factory from a place of brute physical labor into an agile, self-correcting information processing engine.